Okay, so hello everyone. My name is Mateusz Kubuszok, and I will be showing you this little presentation with a really long title: Slow Auto, Inconvenient-Semi, and Escaping the False Dichotomy with Sanely-automatic derivation. So we will explain all of these weird words in a moment. I know it sounds overwhelming, but bear with me. So a little bit about me. So I've been working with Scala for about 10 years. Quite a lot to get some experience. Eight of these years were spent with Chimney, which is like macro-heavy library, which make me learn a lot more about derivation that I wish to know. But I was also blogging in the meantime and wrote a little book about Scala and JVM, things you should know about JVM if you're actually working in Scala. But let's get back to the main topic of our presentation. Basically, we will want to explain first what is a type class, because this thing is basically the core of the presentation. That we in Scala are using type classes. They are core to a lot of the libraries in ecosystems that we are using, and a lot of people are using them, but not really understanding how it works under the hood. Why should they? Then there's this matter, the things called type class derivation, which is really tied to this type class, and for a lot of people, it's not a clear topic. And for a lot of people who see this concept for the first time, they might think it's something about integrals, and no, this derivation have nothing to do with calculus. Then there's the thing called automatic and semi-automatic derivation. So we will have to talk a little bit about that. Where is there a difference, and why the difference matters? Because apparently it might matter. Then we will see that some libraries are not exactly following the distinction that. Okay, I'm going to say Kirke. This is what is from Greek. I know that you adjusted to the CRC, but I'm just call it Kirke. So Kirke set up certain pattern that a lot of library followed. Kirke propagated this whole way of how we are using type classes and how we should implement them, and how we should use shapeless and whatnot. But not all of the libraries are following this pattern. One of the examples is JSON, and the other is Chimney. And once we see all of these examples, we will try to ask one simple question: how of the choice of the library maintainer, how they're going to implement their library affect you as a user? Because in this whole presentation, we will try to focus on this single question, how does it affect you, not how it affects the library development, whether the library maintainers are happy, but how does it affect you if you are the users are happy with what the library does with all this type of derivation stuff. And also because it would be too much code to show to all of you, how I'm deriving things, and this is not the main topic of the derivation. You want to only care about the results. If you want to look at the code of the derivation, please use this QR code. I will show it also at the end of the presentation, and there you have all the code, all the benchmarks, all of the stuff for you to check. So I will show this code once again at the end of the presentation. Okay, so let's get to the type classes. What it is, for those of you who never heard about it. Well, first of all, it's an interface. Good old interface that we or someone else have to implement. But it's an interface with type parameters, because we want to distinguish two different implementations of this interface by its type signature. So two implementations need to have two different type parameters applied. And there's also this neat little trick that if the implementations are distinct by the type parameters, we can also might try to provide implementation based solely on the type parameters. That's the trick that we're exploiting here. So let's see an example of how it works with encoding JSONs. We have a simple trait encoder. You shove it some data in, and it would turn it into a JSON, where JSON is some representation of JSON as a data as a separate type. Then we have some implementations which are supposed to handle strings, int, doubles, just for the example. But without getting too much into the details how we would actually implement this stuff. Then we have some extension methods, because it always makes things much more useful if we had extension methods as opposed to applying things manually. And then we could use the stuff with the implicit, which is the stuff we have in Scala, providing values like with implicit context. So we can see that we have a string, we call an extension method on it, and then compiler provide for us the implementation that would be able to like encode this string. Same for the integer, same for the double. Okay, so this is basically how type classes are supposed to use. Different implementations for different types provided for us automatically based solely on the type. But what if nobody wrote an implementation for your particular type? Like here, someone wrote the encoder for string in double, and that's why it works. But if nobody wrote it for you, and you have, for instance, address, user with some values, you try to create those values, encode them as JSON. When then you get an error that, sorry, there is no such implementation that we could find and used so that you could encode your values. And we would like the stuff to work out of the box. And this is the part where type class derivation comes in. And this is this nice little scary, colorful diagram which you can ignore if you are not spending too much time implementing this stuff. What is important for us is the idea that we will somehow put into this implicit scope implementations for the types that we don't want to write ourselves. And it's going to figure out everything based solely on the type. So if it's like a case class, it will look at the fields of the case class and what are the types of each of the field, and somehow out of that, it will figure out how to provide the implementation for this whole case class. If it's a seal trait of an enum, it will see what or it's like subtypes, get the implementation for each of the subtypes, and combine them together into this implementation of a whole type. And that's the general idea, and yeah, that's basically it. But the devil is in the details. So when we look at the Kirka, how the Kirka approaches this idea. Okay, so again, we have the encoder, we have the extension method, we have some case classes that we would like to generate the implementation out of the box with no manual intervention. So this is the implementation that we are looking for. Like, we want to have something which would take address and generate this exact JSON, and it would take user and generate the JSON that you can see. So we can use the names of each of the fields as the keys in the object, and the value should be encoded, recursively. We see strings, so it should be encoded as a string, etc. So one of the ways that Kirke is promoting how we would implement the stuff is through automatic derivation. The idea is that we're getting one magic implicit import, and this one magic implicit import somehow figures out how this is supposed to work. We're calling this as JSON. This as JSON is summoning encoder for address, and this single implicit somehow under the hood figures out that if it sees this case class, it's going to provide the implementation that works exactly how it's supposed to work in the example above. The other approach is something called semi-automatic derivation. And the idea is that, okay, we don't want to write the code ourselves, but we don't want for those instances to pop up magically. We want to control when and where they are appearing. So we want to tell the compiler, okay, this is the place when you are supposed to generate this implementation, but it is on me to take this implementation and put it into some implicit. And because of that, this automatic derivation, semi-automatic derivation, has to handle this tiny little issue that we don't want to have, cyclical dependencies. We don't want this derive encoder to resolve to address encoder, because then if we would try to run it, we would have, infinite stack trace, infinite loop, infinite recursion stack trace. So it has to generate this implementation, but without looking if there is some implicit implementing that in the scope. It has to explicitly ignore it. So, if we will try to generate this address, how it would be supposed to work is that it would have to first, if the user provides the implementation they set themselves, we would like the compiler to prefer it rather than tries to generate it ad hoc, because if we define it once in some place that it's accessible everywhere, we wouldn't like compiler to always generate it from scratch every single time. So compiler always has to prefer the existing implicit that we put somewhere and it's visible to the implicit resolution. But if it's not visible and the implicit for the automatic derivation is in the scope, okay, then it's a fair game to generate this implementation out of the case class. So then some mechanism would have to look at, okay, is it a case class? No. Is it not a case class, not a sealed thread, nothing that we are supporting in this automatic mechanism. Okay, then we are saying simply, sorry, we cannot derive the stuff. If it's, however, one of those few types that are supported by this automatic mechanism, and then basically has to follow the logic like, okay, it's a case class, and we have to, use the mechanism for every single field inside. Okay, so I have to find the implementation for the first field of the address, then implement the for the second field of the address, etc., and then we can combine them together with the information how those fields are named. In the semi-automatic derivation, it's very, very similar, except it's not a fallback. It always, even if there is some implicit with address in the scope, we have to ignore it, because if we wouldn't ignore it, usually we use the semi-automatic derivation. We want to get the value and put it in ourselves into some given. So if it would be looking for some implementation, then we would have infinite recursion and we would have a problem. So it has to explicitly ignore every possible existing implementation for this particular type to return a new implementation. But while creating this new implementation for every single field, it has to look for some existing implicit that would implement those nested fields or nested subtypes. And we can see that when we move to the user, which is case class, which is nesting another case class. Okay, so this whole pattern repeats. So we would have to check if the user exists. It's not existing. Okay, we are deriving it. Okay, we need to find a field for every implementation for every single field of this user. Okay, one of the fields is another case class, so we don't have this defined as an explicit implicit. So okay, we have to also generate this implementation for this address and so on. So this is how it would work if we're derive automatically the implementation for the user. Semi-automatically, we are skipping the part when we are trying to, find the existing implementation of the user, but we need to find implementation for every single field inside. So if we don't have this imported magical generator for all of our implementations, we usually end up in a situation when we are defining implicit for every single case class somewhere at some points that it could be fetched and used. That's the basically general idea of how those two patterns work in Kirke and libraries which are based on Kirke approach, whether it's implemented in Shapeless or Magnolia or Mirrors, whatever. If you are following this approach, basically this is how it's going to work. The detailed code of how I would implement those implicits. Again, we're skipping it for the implementation once before it, because it's not the part of the topic. We only want to focus on how whatever library implementer is doing affects you. Also, reminder, you can just find it in the repository because it's not relevant for the presentation, only the outcome is relevant. And also, if we actually dig deep into how the Shapeless works, how Magnolia works, how Mirrors works, etc., then we will spend next 3 hours, and probably you all would be scared, but we wouldn't get anywhere. So just skipping this part. Okay, so why people even bother with this distinction between automatic and semi-automatic derivation? Sorry. One of the reasons is that why you might want to use semi-automatic derivation is that the best way to ensure that you have the same implementation used everywhere is simply putting it into a single value and then using this value everywhere. Then by design, you are using everything the same implementation. You have consistent behavior, which matters if you need to use the same implementation in a lot of places. If you only have to derive it and use it in a single place, it of course doesn't really matter. But if you are reusing the implementation and you want to have the consistent behavior, well, the simplest way to ensure it's just basically deriving it once, putting it in a single place, and then reusing this single implementation everywhere. This is undisputable, and I'm gonna dispute it. But the other reason people are using it is speed. So let's take a look at this example right here. So we try to do so. This example simulates something like round trip with a JSON. We are taking some value, So I coded it out because the output of the test. This single value would be encoded as JSON, then it would be decoded as JSON, and then we would return it. One of the reasons is maybe in our unit test we would like to just check that encoders and decoders are matching each other. Like we take it as a given, but sometimes someone might mess something up, and we might end up in encoders and decoders that don't combine into something that's supposed to work reasonably. So because I'm very, very mean for the compiler, are designed. This is like a really, really nested case when I have a case class, and this case class has a single field. The single field is a case class which has a single field, and I basically designed this 5-level nested deep case classes. So it isn't like something really, really complicated. It would be just something like out case class with a field which is like in5 case class, which would be containing in4 case class, etc. Like very, very simple code. It is like completely meaningless, but if you look at it, you could think like, okay, it's very simple, then it should compile fast, work fast, etc. Right? So, yeah, with semi-automatic derivation, you would have to write it everything manually. With automatic derivation, you would, we wouldn't have to do this. That would be enough for you to, run this test. So how it affects compiler? So on Scala 2.13, the difference is not that much. On Scala 3, the difference is, becomes noticeable. Remember, this is, a single implicit derived to use only a single place. So yes, this particular case class, 5 levels nested deep because, on purpose design the derivation to be very, very taxing the compiler because I know how shapes work and things like that. So you can design this single file, which would be compiling on Scala 2.13 for 12 seconds, something like that. Single, very short file, compiling for 12 seconds. There is no difference between automatic and semi-automatic derivation due to a lot of optimization. We'll talk about later. But when you look at Scala 3, the difference is there because this file that I designed was compiling for over 40 seconds. Meanwhile, semi-automatic derivation was compiling only 10 seconds. So, you might think that there's something going wrong. If you probably look at Scala 2.12, you could see similar things to Scala 3. Because in Scala 2.13, there was a lot of optimization put into place, and people remembering those times remember that they could have exploding times of compilations simply coming from the fact that they were using automatic derivation. So the semi-automatic derivation was a users trying to fix the problem with long compilation times when they try to use the derivation. And it was partially solved in Scala 2.13, but it got back in Scala 3. So this distinction kind of matters, unfortunately. You don't care if you are using those two things together, but then you look at the compile times, and you can see that you can accidentally design a single combination of a case class that could explode your compilation times, and then you are basically struggling to find this single place of code when you have to cache things manually so the compiler would not struggle for several minutes. So that's one of the reasons. The other reason are the benchmarks. So when you compile the benchmarks of how this code, remember, a single round trip, encode JSON, decode JSON works. On Scala 2.13, due to optimizations, you see the difference is not that much. The throughput is somewhere along the same, order of magnitudes. But on Scala 3, something interesting is happening because automatic derivation with Circe is 10 times slower. Again, it's very mean design of the case class which triggers this behavior, but still, you shouldn't be able to have such a mean design of a case class that if you run CodeGen on top of it, you have 10 times performance decrease. And that's something that we can observe. Okay, so that's one of the reasons why people decided to use semi-automatic derivation. They basically were solving their performance issues. On Scala 2, however, we can see that the difference are not that big because there were several PRs made by Miles Sabin who were trying to fix this. There was several attempts which failed, but finally he merged it somewhere before 2.13 was released, which is why if we are using the implicit in a single place, the caching of the implicit works, and automatic and semi-automatic is not that different. Scala 2.12 or Scala 3, the difference still matters. And as we could see in the PR, which was merged for the Scala 2.13, we can see that more Sabin observed that comparison in how much time it took to compile, before and after the automatic derivation, you can see that the improvement could be quite significant, like from 400 seconds to 16 seconds. Still, 16 seconds is quite a lot, but better than 400. Okay, could we do something else to improve the performance, like other than automatic, semi-automatic derivation? And this is the question that was asked by someone who implemented Magnolia. One of the reasons Magnolia was provided was to give better user experience to people who are using those libraries based on typeless derivation. So it was supposed to be an alternative to shapeless, and when Scala 3 appeared, also alternative to mirrors. It boasts about better API, because let's not dig into the details, but it's supposed to have better API for the users if they want to implement anything based on typeless derivation. It should have better performance, better compilation times, and better error messages when the derivation fails. So let's start with the last claim. I hope you see it. We have some 3 nested case classes, and I purposefully made one of the fields, if the most nested one, something that we don't have implicit for. So it should fail derivation. If we try to derive encoders for all 3 of them, we want to try derive encoders for all 3 of them, and then compare the errors that would be given to us if we did this with shapeless, or with mirrors, or with Magnolia. So with shapeless, we get an information that we couldn't find an implicit lazy value of some type. So it's not really helpful. The only information we're getting that, okay, this particular implicit fails, so we have to manually look, okay, which of those fields might be something that compiler couldn't resolve implicit for, and figure out that, okay, this particular field has to be handled in some way. We only see which type failed, but not which field of this type failed. Mirrors, well, mirrors are slightly better history, because they are telling us that we failed to find an instance of the either string or nothing. So at least we know, okay, this is the particular implicit that failed, so we can fix it. We're not sure in which class, but probably we can get it from the context lab, because we've seen that it's in the street encoded, so at least it's something. Magnolia's error was something generated by the macro, so we're saying that, okay, we couldn't create a type class we couldn't find a type class for the either string or nothing, and it was used as a parameter. We would need to have it resolved, because we would need this to handle the field name of the field street. So very good compiler errors. It would let you figure out immediately, okay, what went wrong, how to fix it, where to put some additional implicit, or which type you need to fix manually, so that things will compile again. Okay, so there's an improvement. But with automatic derivation, all 3 of those libraries are telling you only that there's implicit not found. So all the benefit of figuring out which of those fields is preventing your whole nested hierarchy to compile is completely gone. So the user experience for automatic derivation, if the failure is somewhere deep, it's really, really bad. You just see that the top level couldn't be derived, and it's up to you to figure out how to debug it. Okay, it's a reminder that before we try to this round trip. So let's get back again to this round trip example with encoding and decoding JSON. But this time, let's add Magnolia to the benchmarks. So we could see that, at least on Scala 2.13, Magnolia has very similar compilation times to shapeless, due to all of the effort put into the shapeless, instance caching, etc., etc. Before that, if you were using Scala 2.12, you could see some examples when Magnolia was compiling faster. But the interesting thing is what is happening with Scala 3, because we can see that Magnolia is taking more to compile than raw mirrors. So if you try to use this better API, which is supposed to give you better experience, better performance, etc., you can see that, well, at least when it comes to the compilation times, it increases the compilation times as opposed to using raw mirrors. And it's like easy to explain if you remember, if you look at the code and see that Magnolia on Scala 2 was implemented with macros. So it only had an overhead of running a macro, while on Scala 3 Magnolias are implemented with mirrors and some macros. So all the overhead of working with mirrors, plus some extra overhead of adding those stuff that is missing from the mirrors. And at the end, it's visible in the benchmarks. But if we try to run the code and see how it performs in the runtime, interesting things happen, because well, we can see that semi-automatic Magnolia, for some reason, has better performance than mirrors on Scala 3. Apparently, the structure that is derived by Magnolia is much more friendlier to the JVM and how it works, but only if we are using semi-automatic derivation, because if we are using automatic derivation, both on Magnolia and mirrors, we're getting this decrease in performance, but for some reason we can see that Magnolia has even more performance decrease than raw mirrors. So it's could butcher or application's performance in some very bad cases. Like normally you shouldn't have this much decrease in the performance on purpose design. So very bad example, but you can have such an example by accident just by using very rich models in your domain, and then you can end up with, well, not only 10 times decrease in the performance, but even 100 times decrease in performance. Okay, so did someone else try something else than shapeless mirrors Magnolia? And if we are talking about JSON decoding, for starters, yes, someone did. JSON inter Scala. This is a library which is focused on performance, and it also has no automatic derivation. But it's not an issue because you do not have to provide the intermediate type classes. So if you have this deep nested hierarchy of case classes and you want to derive the topmost one, it can recursively derive the code that would handle the intermediate case classes. And you don't have to provide implicit for it. So even though you are using semi-automatic derivation, you still have the benefit of handling things recursively. You don't have to write a code for every single intermediate type. So it's really useful. So when we see this code, we have to modify it a little because we have to basically use this semi-automatic derivation. It also has slightly different API than the CRC, but when we run it, as I said, when you were asking to derive the codex for the top level type, it will go through all the nested fields. And for each of those nested fields, if it sees that it also has to derive the implementation, it will derive it so that you are getting the end product, not something intermediate. Yeah, let's skip that part because we are short on time. Okay, there was a lot of gibberish about how it's supposed to work, how it's working under the hood. What are the numbers? Well, the numbers are that Magnolia JSON is much faster than anything that we can achieve with Kirke, whether it's automatic or semi-automatic derivation. Benchmarks show that it's much better. Those are for now benchmarks for the compile time. So this approach with semi-automatic derivation, but which is recursive, not only on the top level, is compiling much faster than both approaches when you have automatic derivation, which is recursive, or semi-automatic derivation, which is not recursive. This approach beats both of them when it comes to speed of compilation, but also beats both of them when it comes to speed of the runtime. For this particular example, we are seeing that JSON inter is twice as fast, maybe sometimes 3 times as fast, on both Scala 2.13 and Scala 3. So yeah, we can see that something is happening. Maybe it's worth investigating. But of course, we will still have to derive these instances and put them into implicit yourself. And sometimes, in some a lot of cases, you will still want to have automatic derivation because it's much more convenient if you don't have to remember about running some codec, putting it into implicit, making sure that you have to import it. You would prefer to, normal cases, just import stuff and just use it. It would be much more user-friendly, and so that the caching will be something like edge case, not a common case. So this is something that we had in a chimney. We also had a problem that we wanted derivation to be recursive, so that we would give good performance, but also good error messages. But we also wanted users to be able to provide some implicit to override what we are doing in a macro, because always users provided implicit should take precedence over what we are doing inside the macro. Macros should handle defaults, and user should be able to override with their own implicits or whatever. But we wouldn't want to break those two assumptions by providing automatic derivation. And in the naive automatic derivation, when you are just putting everything in the implicit scope, okay, let's see if user provided some implicit. Oh, we are finding our own macro, let's expand it. And then all of the benefit of recursive macro derivation is gone because we'll be finding our own implicits. So I came up with this nice little pattern. I hate it, I admit it, but with this nice little pattern, I am able to force a situation when if user is providing their implicits, they are being used. But if I am looking for implicits and the only implicits in the scope will be the one I provided, it would be ignored. And with that, I am able to just derive things recursively and only use users' implicits to override this behavior, the default behavior. So, yeah. But you don't have to look at this pattern. It's just, for the curious, you can ask me about it later on. The question is, can we use outside the chimney? Because we want to be able to know whether those things can be, generalized, or is it some observation just for a single library? And the answer is yes. So for this presentation, I first wrote a wrapper around JSON eater. It's Scala-free only for some reason, but for many reasons, but it's just a POC. And with this wrapper, you are able to just get symbol import, and with the symbol import, you're going to automatically derive instance, but this instance would be derived recursively. And because it's derived recursively, when we compare it to CRC or normal JSON eater, we can see that the compilation times are it's only a Scala-free. This is the blue bar on the right. The compilation times on cold JVM are only slightly worse, but still better than whatever you're getting for semi-automatic derivation of Kirke. But on hot JVM, basically you see no difference. So you have all the benefits of having an automatic derivation, but without all the overhead of automatic derivation. Similarly, in the benchmarks, no difference between this wrapper of mine and vanilla JSON eater. So it seems that we are onto something. But still, someone could argue, okay, JSON eater was designed with the performance upfront, from scratch. This library is not doing a lot of stuff that Circe is doing. It's not using intermediate structure for JSONs. Circe is decoding things into JSON, and then those JSONs are passed into the decoders to create this target value. Which basically means that if we try to decode strings into target value and back, then we probably could, have even bigger difference between JSON eater and Kirke. But if we want to talk about some, more fair comparison to see how it works in, some different examples, some different cases. So yeah, I decided to do more fair comparison. So this is basically a show class from the cats, but on steroids. In cats, you have something which is like a type class, which is supposed to be used like toString, but more safe use string, more one which is able to handle arrays safely, when you can override some stuff to I don't know, redact some fields out, or provide some better support to more pretty printing, things like that. So I decided to implement something like that. Show instance, which is much faster because it's using string builder, but which is also using this pretty printing, so that you have all of these indentations, things like that. So it's much more user friendly. And then once I designed this API, I implemented in with shapeless on Scala 2. Then I implemented it with mirrors on Scala 3. Then I implemented it with Magnolia on Scala 2 and 3. And then I use also Chimney macro commons to implement this Sanely-automatic derivation on both Scala 2 and Scala 3. And then run the benchmarks and see how it goes. So we can see that, well, the results of Scala 2.13 are like quite comparable. So we have the convenience with roughly the same compilation times and roughly the same compilation time on Scala 3. It seems to be, at least this example, it seems to be slightly slower than vanilla semi-automatic derivation, but much faster than automatic derivation. So you have the benefits of not having to put manual implicits everywhere, but you still could do this. It's just this is now an option, not something obligatory to do everywhere. When we run runtime tests, we can see that on Scala 2.13 the results are quite comparable when it comes to the speed. We can also see that once again Magnolia and automatic derivation and mirrors and automatic derivation are doing pretty poor job. So semi-automatic derivation is much better. Or sanely-automatic derivations, I prefer the name because it's automatic derivation done in a sane way. It's sanely automated. But there are some more benefits that, but I forgot about something. Basically, when JSON iter does its derivation, it's cache the intermediate results. Like if it derives some code, instead of deriving it again when it meets the same type to handle, it puts everything into private defs. Inside your big definition, you have some smaller defs, and this way it caches the intermediate derivation results so that it can reuse it and derive some operations only once. Also, the JSON uses it so that it could handle recursive data structures because if you have several defs inside a bigger def, you can call one of them, call another, etc. So you are handling recursive data structures. So when I ported this solution to our code, I could see that, like before, it was sometimes slower than semi-automatic derivation, but now I'm faster. So it's always better. And even when I'm running the code, it's always faster also in the runtime. So with a single change in the macro, I was able to beat up several years of optimization of the compiler on Scala 2.13. So this is optimization that I can do anytime without waiting for compiler team to catch up with me. So this is a huge benefit of using macros. But there are also some bonus stuff because if I'm writing my own macro, I'm in the control of the errors. So I can write error messages that tell you how to fix if things are not working. And if I'm doing it recursively, even if I fail the derivation in the somewhere 10 levels in the depth, I am still able to tell you that, okay, this derivation failed because this class is using this field, and you provided me no support of such fields, so you have to do this. So I could, derive this class again. So as a macro developer, I am able to give you much better user experience when it comes to fixing errors, error reporting and stuff, than what Shapeless and Mirrors and Magnolia does, whether you are using it automatically or semi-automatically. And also, if you are approaching writing macros as you are approaching writing services, you want it to be debuggable, you can also do something like, okay, if I have this flag, I could write this message for the user so that I could see what is the logic inside macro and what is the final expression and what is how much time it took to derive stuff. So you could, inside the macro, write the exact logic, write very detailed logs, give it to users so that even if things fails or a user wants to have more in-depth knowledge, why you derive the code the way you derive if it succeeded, you could give it to your users very detailed log you could see, and the compiler for a long time had tools that you could show it, not only in the SBT. You could show the stuff like in your IDE, when you hover over the places that is expanding the macro, then you have the information. Okay, here, this is the info diagnostic from the compiler. Those are the logs from the macro expansions. And then you, as a macro developer, could give your user information how the macro was derived, what were the decisions that led to the exact expansion, give them the exact expressions that you derived, so they don't have to use some weird compiler flags to preview the code. You could just provide them as a debug utility for your own library. So I am slowly finishing the only things.
Slowly, Mateusz.
Yeah.
15 minutes ago, you said that you were running out of time.
Yeah, yeah. So if you are just curious if something changed since last version of Scala, then on Scala 2.7, well, this pattern of mine stopped working. But however, the compiler team was so good that they gave us some utilities that I am able to, write much more direct code. So then I could, fix the code so that it again works on Scala 2.7, even though there were changes to how the givens works. And after I applied this small little change, I could run the benchmarks. And after I run the benchmarks, I could tell you that the results are exactly the same. So if you are asking if the new version of Scala are fixing things or changing things for us, sorry, no, compilation times are still as they were, and the benchmarks they are still the same as they were. So yeah, in both examples, whether it's comparison of JSONs or where it's the comparison of this show pretty example. So yeah, I have to finish finally. So thank you for the talk, and I hope that this talk encourages you that you should demand of your micro library maintainers, or sorry, every typeless derivation maintainers more, because you can have faster compilation times, faster runtimes behavior, and better error diagnostics, and better messages how to fix things if they are not working, which is helping you deliver more value, helping you give much more bang for the buck for the code you're writing, and this is all possible. Compiler don't have to be slow. It's just library maintainers. I chose this slow path because all the libraries that existed so far prioritize the library maintainer experience over the user experience, and this is something we can challenge to make Scala more popular again, help us all keep our jobs and stuff. So yeah, thanks.